Okay, so why don't we go ahead and get started? I'm very excited to present to you Caleb Christensen, who is going to be defending his dissertation today, and is actually the first student from my group to defend his dissertation, or hers. Although Caleb is actually in nanoengineering, so this is, a little bit of a maybe slightly different talk from what you would typically see in a nanoengineering presentation. Hopefully, those of you here from nanoengineering will appreciate the connections. So Caleb started at UCSD, when was it, 2013? Fall 2014, so around the same time as me, and then joined my group about a year later. And yeah, I think I'll leave it at that. We're going to have a talk which will be about an hour. If you have any questions, please feel free to ask them if they're urgent questions. But if you want, we'll have a little bit of time at the end for discussion, and then we'll ask the general audience to leave, and the committee will have time to speak with Caleb on our own. Okay? Any questions from the audience before we begin? Okay, great. Please take it away.
Thank you, Mike. Well, thank you all for coming. Glad to see so many friendly faces on a early morning. Also, thanks to the committee for spending their time and expertise and helping us get through this. So, like Mike said, my name is Caleb. I'm working on my PhD in nanoengineering, and the topic for my dissertation is actuation for bioinspired soft swimming robots. As kind of a brief overview of some of the other projects that I worked on while I've been here at UCSD, I started in Joe Wang's group, where I worked on micro and nanomotors for drug delivery and environmental applications. So the first one, we used red blood cells to swim around inside bloodstreams to deliver chemotherapy agents. The second one was micromotors that were driven by vapor propulsion. Then I joined Mike's group and worked on a few different projects. First one is on 3D printing for material that can, it's soft. It's a combination of soft and rich material. So the base of it is soft, and it can inflate to apply point pressures. So the base of it's soft, and then the tips of these teeth are rigid. So even though the body that's soft and flexible, you can still apply point loads and break something like an egg. Also worked on some shape memory polymers, worked with Ben and our group on stretchable sensors using carbon nanotubes, then also with 3D printing, flexible electrodes. Then I started working on DEAs, so dielectric elastomer actuators, which is kind of the basis of this talk, most of this talk. Then I spent a summer at JPL, where I worked on using electrostatic forces to make a spacecraft orbit around this small body, like an asteroid or a moon. I also used DEAs to work on fluid pumps, and then the talk today will be focused on these last three projects, where the first one is this eel-inspired robot based on dielectric elastomer actuators, and then a jellyfish-inspired robot based on DEAs, and then finally a cephalopod or a squid-inspired robot based on a method for slowly storing and quickly releasing elastic energy. And there's kind of a theme here at least the last three projects. I kind of found fluorescence as an interesting research tool, and also it's kind of captivating. So if I was an artist, this would be my fluorescent period, which is what we're going to be talking about today. All right, so why soft robots? Why soft swimming robots? So if you want to study something underwater, it's often dull, dirty, or dangerous to send a diver there. So instead, many times we opt to send robots, such as autonomous underwater vehicles, or AUVs, like what we have here in yellow on the left, or ROVs, remotely operated vehicles, like this guy here on the right. And so this allows us to send a robot instead of a person to do jobs that are too dull, dirty, or dangerous for people to do themselves. The trouble with sending these big AUVs and ROVs is that they're made out of rich materials. They can be quite large. They're often driven by propellers or jet thrusters. And so some of the challenges with these are that the propellers, for example, could get entangled on kelp or tethers that they have. They could also cut marine life. If they run into something moving at a high rate of speed, they might damage or crack a coral reef. So we're looking at bioinspired actuation approaches to eliminate the need for jet propulsion or propellers to try to obviate some of these problems. Two recent examples for bioinspired soft robots. are this project from Actuate, where it's a hydraulically actuated soft robotic fish. So they have a pump, and they have a pump in the back of the fish that controls these two muscles that makes the tail of the fish swim back left and right. And then there's also this group from Florida State that worked on this hydraulically actuated jellyfish-inspired robot. So it pumps fluid into the arms of the jellyfish and causes it to swim through the water. So a lot of soft robots are based on hydraulically or pneumatically actuated robots. And some of the challenges with hydraulically or pneumatically actuated robots are that you need a pump on board, which can take up some size and weight, and also consumes a lot of power. They can be quite noisy, so it makes a lot of noise and vibration. And so if you want to study something underwater that is sensitive to noise, so if you're trying to measure acoustic signals underwater, or if you're trying to sneak up on a fish, if you have something that has a pump running, you might scare it off before you get close to it. So we looked at 3 different animals to serve as inspiration for our robots. So the first is the eel. So eels are able to swim for a long period of time because they don't use a lot of energy while they swim. What's interesting is would anybody believe that there are transparent eels? Have you seen a transparent eel that look right through it? Okay. If you don't believe me, I'll show you here in a little bit. They undulate through the water, so they have a sequence of antagonistic muscles that cause them to wiggle their way through the water. Does anybody know what the most efficient swimming animal is? Shout it out.
The eel.
Yes, there's a more efficient swimming animal. What's that?
Jelly.
I heard jelly. Yeah, the jellyfish. So in terms of cost of transport, so the amount of energy that it takes to swim a unit mass per some unit distance, the jellyfish is the most efficient animal. And one of the reasons for that is that instead of having antagonistic muscles, where like with the eel you have to actuate muscles to swim to bend the body this way, actually the other muscles to get it to swim the other way. With the jellyfish, since it's elastomeric a little bit, it will actuate its muscles to squeeze the belt, and then the elastic restoring force of the body will cause it to re-expand. And so it can consume less power because it's only actuating muscles during the contraction phase, and then it's just passively recovering. So what about, does anybody know what the fastest swimming animal is? The fastest animal?
Shark.
What's that?
Shark.
No. Oh, I'm sorry. Let me clarify. What is the fastest invertebrate? There's like 3 choices, and I've already put this all in on what the animals are talking about. So squid. That's right. Or cephalopod. So I'm going to generalize it and just talk about cephalopods. But the squid is the fastest invertebrate. And so there's a few ways that it does it. If it wants to swim using jet propulsion, it will hyperinflate its body to suck in a bunch of fluid, and then it will squeeze out the fluid. And it will do this in intermittent bursts, so that way it can swim through the water. And then it also has something, it takes advantage of the added mass effect, which means that as it hyperinflates, it gets bigger, and then as it squeezes out water, it becomes smaller. And so you get an acceleration where you can change the size of your body while you swim. So we'll talk about that here in a little bit. All right, so those are the inspirations for these 3 projects. So we have the eel-inspired robot I talked about, and we have the jellyfish-inspired robot I'm going to talk about, and then lastly, our squid-inspired robot. And so the questions that we have are, and that I had, is can we design artificial muscles for a soft swimming robot that are silent, transparent, fully elastomeric, and enable eel-like swimming? The second question that I had was, can we develop an actuator that takes advantage of the energy-efficient pulsatile motion of the jellyfish to enable a low-power, untethered robot? And then the last question that I had was, can we demonstrate an actuation strategy for a squid or cephalopod-inspired robot that takes advantage of both pulsatile jet propulsion and the added mass effect? So I'm going to go into each of these here in a moment. So if we want to make muscles or artificial muscles for soft robots, we want to use a type of actuator that has similar properties. as muscles. And so the actuator that we chose is called the dielectric elastomer actuator, or a DEA. And so it works like this. So a DEA is a rubbery film. So it's an elastomer. And then on the top and bottom of the film, you have conductive compliant electrodes. So you have electrodes on the top and the bottom of the film. And then as you apply a voltage to the film, there's electrostatic forces that will compress the film, so it becomes thinner. It'll also increase in area, so it'll become thinner and more spread out. And here's a video of one of them working. So the transparent section around the outside, so there's a rigid ring on the outside, and then there's a transparent film, and then the black part is where the electrodes are. So then they're applying a voltage of maybe 5,000 to 7,000 volts to get this actuator to move. And so the pressure that you can generate with these actuators goes as epsilon r, which is the permittivity of the material, times epsilon naught, which is the permittivity of free space, and then it's times the voltage that you apply divided by the thickness of the actuator squared. And then the strain that you get, the amount that it moves, is proportional to, or it's equal to nu, which is the Poisson's ratio, which is the ratio of how much it bends in, or it deforms in one direction. And then the same components that we talked about earlier, and it's divided by the Young's modulus. So what this shows is that if we want to get large pressures or large strains, we have a few different variables that we can do, or a few different ranges that we can work with. The first one is the permittivity of the material. So we can select a material that has a high permittivity. So the materials that we're working with are anywhere from 2 to 4.7. The voltage that we apply. So you'll also see that the voltage and the thickness are squared. So there's a higher, there's a higher dependence on the voltage and the thickness of the material than there is on the permittivity. But the voltage that you can apply is limited by the breakdown strength of the material. So like how much voltage can the material take before it sparks and so it breaks down. And then the thickness of the material. So the materials that we work with are usually anywhere from, say, 50 microns to a millimeter in thickness. And then the Young's modulus is something else that we can select for. So if we want to make something that's like a muscle, then we can compare different types of actuators to natural muscle. So one way that we can do this is a qualitative comparison, where across these different categories, we have strain, actuation pressure, density, efficiency, and speed for the response of the actuator. So natural muscle is rated as good across these different categories. So then if you look at some of the other types of actuators that people use, like electromagnetic, it's good for strain and pressure, so you can get a lot of pressure with motors, for example, but they're very heavy, so they're very dense. And also they work better at high speeds than low speeds, so they're not as efficient at a broad range of speeds like natural muscles. But if you look on the bottom where we have dielectric elastomers, they have a similar comparison, similar performance as natural muscles. So it's a good choice for making artificial muscles for soft performance. So if you take a rubber band and you stretch it, this is what the force as a function of stretch would look like. So on the y-axis we have force, and so as you apply more force, it will start stretching out more and more. And it doesn't take a whole lot of force to stretch out a rubber band until you get towards the end, or the stretching limit of the rubber band. And so at low stretches, if you imagine you have, so one way of thinking about this is if you have two balls of chain, and you have a spring in between the two chains. And as you pull on either end of the chains, you're just kind of unraveling each of the balls of chain, which doesn't take a lot of force. And then once you get to the spring and it becomes taut, then it takes more force to pull the spring apart. And that's kind of what we're seeing here. That's one example of how you describe what we're seeing here. So it's very easy to pull at low strains, then as you get farther apart, it takes more force as you're pulling its covalent bonds. For these actuators, if you'll remember, the pressure goes as the inverse of the thickness. And so what's happening is that if you apply a constant voltage, you're generating this feedback loop. So as you apply a constant voltage, you're making the actuator thinner. So if you apply a constant voltage, you're generating a pressure, which makes the thickness thinner, which then increases the pressure, which then increases or decreases the thickness even more. So you're generating this positive feedback loop. And so then the curve, if you plot the voltage as a function of the stretch of the material, it looks more like this. So it takes a certain amount of voltage to get it to deform a little bit, and then after a certain point, it'll start feeding back. Let's see. Yeah. Okay. So as you increase the voltage, you get a small amount of strain, and then right around here, this is maybe around 30% or so. What's going to happen is that as you keep the voltage constant, it's going to become bistable. So you could jump from this position all the way across to the following position at the same voltage. And so what that means is that if you can get to that point, you can actually get very large deformations with these materials. The trouble with that is that different materials have different breakdown strengths. And so if you make the material too thin, it might break down before you can actually get to that snap point. And so for the longest time, people were limited by, researchers were limited by this case here, to where they could get to, say, 30% strain before it would break down. But then what researchers found is that if you stretch the material ahead of time, you can actually change when the material will break down. You can get improved performance by it. But the challenge with that is that once you stretch the material, you need to apply it to a rigid frame. And so then if you apply it to a rigid frame, then you can get better performance from your DEA, but then you no longer have a soft load option, because then you have some plastic or metal implements in there too. So we're trying to look at ways of getting large actuations from these actuators without using free strain. Okay. So the two materials that people normally use for DEAs, one is an acrylic-based elastomer. A very popular choice is VHP. It has a high permittivity. It's also very easy to use, so it comes on a roll. I've got some examples of it over there. But the challenges with this material, even though it's widely used, is that it comes in only discrete sizes, so you can only get it at a few different thicknesses. It has a high relative Young's modulus and a low breakdown strength. Okay. On the other hand, other people choose to use silicone-based elastomers. So this is PDMS. So many groups use this for microfluidic strips. You can also use it for DEAs. And so with PDMS, you have better control over the thickness, because you can spin coat it and get really, really thin layers of it. It also has a lower Young's modulus, so you can get higher stress or sex rate. And it has a higher breakdown strength, so you can apply more voltage when you're trying to actuate it. The trouble is that it has a lower permittivity, so it's almost half as much as what VHP is. So in our work, we are focused mostly on VHP because it's very easy to prototype with. But then for further improvements, we might move to maybe a more silicone-based.
Okay, but we forgot the units on the left here, right? So this is also megapascals? Yes,
that is true. That's the type of thing. Yeah. Okay, so that was the material for the elastomer. The other material that we need to consider is for the electrode. So you want a compliant electrode, so something that can apply electricity but won't change the material properties of the actuator. And so what many groups use are carbon-based electrodes. So the one on the left is carbon particles. So if you have graphene or carbon nanotubes, you can just apply them directly to your actuator, and that will conduct the electricity. Or you could use carbon grease, so it's carbon particles suspended in a grease. But the trouble with the grease is that it will actually permeate through the elastomer and change the mechanical properties of the elastomer over time. And then other people will use an elastomeric matrix. But the trouble with the elastomeric matrix is that it can also stiffen your actuator, so you can get less performance within the structure. But instead of carbon-based electrodes, what we could look at is, so another issue with carbon-based electrodes is that if you want to make something that swims underwater, you need to encapsulate it from the surrounding water, or else it will short out to the water. And so what many groups do is that if they use carbon-based electrodes for DEAs, but have to add an additional encapsulating layer on the outside to keep it from shorting out to the water. We'll come back to that here in just a second. So use carbon-based electrodes, you have a stiffer structure, generally speaking. So our motivation was to mimic the motion of an eel. So I told you that there's a transparent eel, and here's a video of it. So the larval stage of an eel can be transparent, and it wiggles its way through the water like this. So we wanted to know, we wanted to see if we could actually make a software robot that would be transparent like the eel. And so one way of doing that is instead of using carbon electrodes, and we use ionic electrodes. So this example from Harvard is where they use a ionic hydrogel to show that you could get high-speed actuation with ionic hydrogels. And then another group used water as the electrode in a microfluidic strip. So they use water to apply the electricity to the microfluidic strip. But up until now, nobody's used water as electrodes in a robotic. So I told you this question at the beginning, so I'd like to show some of the hypotheses that we're trying to test with this robot. So first hypothesis is that we can use water for both electrodes in a DEA. At high voltage, we can even use pure water or nearly pure water to be conductive enough for actuation in a DEA. That DEAs without restrain can generate enough force and strain to enable underwater propulsion. DEAs can be used for completely silent swimming, so you won't have the motor noise that you would get from an ROV or an AUV. And then DEAs with fluid electrodes can be made to be as transparent as an eel. And then lastly, for fun, transparent fluid electrodes can enable fluorescence. And also, if you notice that it's shaking, it's because the construction is vibrating the projector. So it's not you, it's the projector. Lastly, a series of bimorphic DEAs can generate field-inspired undulating locomotion. So how do we do it? So I made a bimorph actuator for the eel-inspired robot. So the bimorph means that it can bend in two different directions. And what we have is we put this in a tank of water that's grounded. So it's connected to ground. And then we have fluid pouches inside this actuator. So in green here, this green on the inside is water, and there's 3 layers of a dielectric elastomer. And so what happens is that as we apply a voltage between one of the pouches and the outside water, it will compress the actuator, one side of it, and cause it to bend one way. Or we can apply the voltage to the other actuator to bend the other way. So to test this, we put it on a simple test stand, and then apply the voltage to guide it to move. So we can control the direction of bending based on which pouch we apply voltage to, and then we can control the magnitude of bending based on the amount of voltage that we apply. So then we also compare this to an analytical model that shows that the curvature should be proportional to the Poisson's ratio times the permittivity times the voltage squared divided by the Young's modulus and the cumulative thickness. And show that our experimental results match up pretty well with the model that we have. So then we also wanted to see if we could get this to swim through the water. So this is tethered swimming, just a single bimorph actuator. So I'm applying voltage to both sides of the actuator to get it to wiggle its way through the water. The trouble with this guy is that in order to get an asymmetry, in order to get to swim forward, we needed to make part of the actuator more rigid than the other part of the actuator. So we put a zip tie on the front of it to provide some asymmetry, and then also it mostly swims when it can kick off the surface. So it's kind of like an inverted water strider. So that works. For that, I also wanted to compare it to carbon grease to see if how water compares to carbon grease for an electrode. So I made 4 different actuators. The first 2, black and red, are carbon grease. The first one is in air, so there's no fluid damping. The red one is when we put the carbon grease actuator into water, and it becomes the amplitude becomes a little bit smaller. And then I compared USP grade, which is very pure water, as opposed to very salty water. And so in green, we have very salty water, and you can get the most actuation performance from it. But then we also tested it with pure water, and we can still see some actuation from it. And so for our test, to simplify some of the manufacturing, we just use deionized water as a starting water for our test, instead of making salt water every time. I said that we can make it silent, so we put a hydrophone in the water next to the actuator and compared the signal when it was on versus when it was off. And the level as a function of the frequency over the audible range, it shows that you basically can't hear the actuator, so it's completely silent. Also wanted to say that it was transparent. So the top two pictures are the actuator over two different backgrounds. One on the left is aquarium rocks, and the one on the right is sand. And so the red outline shows where the actuator is. And then the bottom left is a microscope image that we took of a leptocephalus, or a baby eel. And we recorded the amount of light transmitted through the eel and the actuator. And that's what we plot here in the bottom right. This is the transmittance over the visible spectrum. And there's two different regions of the actuator. There's the active area, which is at the center of the actuator, and then there's the outside border that goes around the outside. And what we see is that the two different regions of the actuator bound the transmittance of the eel. So in other words, it's about as transparent as it can be. So if it's transparent, we want to see if we can do something interesting with it. And we found that there's eels in nature that will biofluoresce. So under moonlight, will actually glow or fluoresce, or luminesce, I'm sorry, bioluminesce. And so we wanted to see if we could capture that with our robot as well. And so we loaded our robot with a fluorescent dye and then simulated it under black light and showed that we could get it to glow. So one of the reasons that they believe that the eels have got this ability to fluoresce so that way they can find each other at night during spawning events. So now that we made it, we want to make it swim. So the way that we made it swim was that that single actuator wasn't enough without having some other force to kick off of it. So we designed a series of 3 bimorph actuators in series to try to imitate the undulating motion of an eel. And so on the right are still frames from the eel inspired robot while it's swimming, and the green sections on the top right show the different actuators that are on or off. So in this one, the back right and the top left actuator are on, so that's why the front is bending to the right and the back is bending to the left. And then we propagate that sequence through the body of the robot to get it to swim through the water. And here's a video of it swimming. This is at 2 times speed. So the average speed of the robot was about 2 millimeters per second. And so one of the things that you'll see here is that the robot is tethered. So there's these 2 tubes coming from each of the actuators that are going to a swinging platform. So one of the ways that we wanted to quantify how well this could swim is that if we just suspended it directly from its tubes, then it would be swimming like a pendulum, which means that it would be going fastest at the bottom and it would slow down as it starts pulling against the tethers. So instead of doing that, we suspended it from a floating arm so that way it could swim at the same depth around a slow arc. So that's what you see here. And then we turn on the black light for it to fluoresce while it's swimming as well. All right, so the results of this project are that we were the first published work demonstrating that water could be used as local electrodes in a DEA for a robot. We're the first paper to quantify the transparency and the sound of a DEA with fluid electrodes. And then that we demonstrated that DEAs without pre-strain can be used for underwater locomotion. So switching gears a little bit. So what we had there was an untethered robot, a tethered robot. So a robot that needs all the electronics off of it because the electronics were pretty bulky to get that control sequence. As an electrical engineer, maybe I could make it smaller if I use PCB and all that. But instead of doing that, what we could do is design a similar actuation strategy. So we looked at jellyfish, which, like I said earlier, it only needs actuation to contract the valve of the robot, and then it can passively relax. And so here's a video of a baby jellyfish swimming. So you can see how it moves. So it contracts these muscles, causing the valve to contract, pushing out water. And like I said earlier, the jellyfish, in terms of cost of transport, which is the amount of energy that it takes to swim a unit mass, a unit distance, You can see that we have running and flying, and then different types of swimming in blue. There's squid here, and then fish, and then jellyfish are the most efficient swimmers across all dimensions. Okay, so the way that what we wanted to do was design this jellyfish-inspired robot. So our hypotheses are that unimorph actuators based on DEAs with a strain limiting layer, so a layer that's inextensible, can enable pulsatile motion, which is inspired by the motion found in jellyfish. That the simple control strategy of the jellyfish enables untethered propulsion. And the way that we design these actuators are similar to the bimorph actuator, but a little bit more simple. So again, this is suspended in a tank of water, so the water is grounded. And then on the top here we have the dielectric elastomer layer, and then we have a fluid pouch again, and then we have a passive elastic layer that the dielectric elastomer sticks to. And then underneath that in red we have a strain limiting layer, which increases the amount of force that we can get for each stroke. And we have tubing that goes to our electronics. And so then when we apply the voltage, what it does is it expands the dielectric elastomer and causes it to bend towards the strain limiting side. The way that we designed this is we wanted to make it layer by layer. So the same way that we made the eel, as we make each layer at a time and then we stack it together. But if you want to make a ball out of planar sections, then you have to be a little bit more creative. So we took a hemisphere in CAD and then took 1/8 of that hemisphere and then flattened it and then designed it as an axisymmetric array. And what this should enable is we can make it flat, and then when we pick it up, it should fold back into a hemisphere shape. And so in here, I showed the two different regions of the DEA. The inside here is the active area in the center, and then around the outside is this passive border that allows the actuator to bring the DEA film to stick to itself and contain water. Yeah.
So for 1/8 of the hemisphere, it is a non-developable surface.
Is it what?
It's a mechanical engineering non-developable surface. Can you make it flat without stretching it?
No. Can I make it flat without stretching it?
What is this material made of?
This
active this passive border and active. What are those materials made of?
the acrylic elastomer, PHP.
Oh, so there are some stretching.
I think the question is how is the second one, the third one.
Oh, this is
without
actually,
stretching.
no. So this is in CAD. So I'm showing you how I designed the design for the layout of the actuators. So the first three sections are all in CAD simulation, or sorry, in design, and then I use that to design the shape of the actuators. So when I make them flat, I want something that approximates a hemisphere when I pick it up. Okay. So I'm not making the first three and out of the film. I'm making the last one. I'm using the last one as a mask for the film. Does that make sense?
The key point is starting from the second, it is curved.
Yeah. Right.
If you want to make it the third one, make it flat, you have to stretch it. If you do not stretch it, you cannot make it flat.
Yeah.
That's the key point.
Right. So we wanted to see, so once we made it, we wanted to get it to swim. So this is a schematic of our test setup. So we have a video camera above the tank, and then it's the jellyfish robot is in red, and then it's suspended by its tube that goes to a float to keep it at a constant depth. And then there's a wire that brings it to the electronics. So this is a video of it swimming. So the red is the strain limiting layer, and then we're actuating it and allowing it to passively relax. So it's actuating, and then as it does that, it will swim through the tank. We wanted to see what the optimal frequency is. So for jellyfish, they show that there is a maximum efficiency if you drive the jellyfish near its resonant frequency. And so what we wanted to do is see if there was a frequency of driving the jellyfish that would also give us the most amount of speed. And so we tested the swimming, we measured the speed of swimming for different frequencies and found that there was a peak speed of believe it's 1.8 millimeters per second at about 22 hertz. And also that's close to the lowest cost of transport. So there's it's most efficient or mostly efficient at high speed at that point. For the electronics, it's based on a very simple circuit. So we have a battery that goes to a switch, and then there's a 555 timer. So the 555 timer creates a low voltage square wave. So it will turn the actuator on and off, and you can control the frequency and the timing of the signal based on the components for the timer. And then the timer goes to a regulator that keeps the voltage constant. That goes into our converter. So we can send 5 volts into our converter, and then on the other end of the converter, we'll get 10,000 volts out. And then we have a resistor that goes across the leads of the converter to discharge the actuator. So it'll charge it up. It'll charge up the actuator, then when you turn off the voltage, it will discharge to the resistor. And here's a video of it actually for the power supply turning on and off. So the multimeter is reading in thousands of volts. So when it's on, when the light's on, it's taking out about 7,000 volts. And so you'll see I brought the power supply over there on the table. If you plug it in, just be careful. So we wanted to show we could connect this to the rest of the robot and get it to swim untethered. So here we are. So one of the challenges with swimming with soft robots is that it's very easy to get it to float because of buoyancy. And so what we did is we first made it slightly negatively buoyant. So we added an air bladder on the top of it to get it to offset the weight of the electronics, but made it slightly negatively buoyant so it falls. And then that's this bladder on the right. And then once it fell to the bottom of the tank, then we turn it on and get it to swim upwards. So this is at 4 times speed as it's swimming. Here's a plot of the position and the velocity over time when it's falling on top, and then when it's swimming on the bottom.
So this is the dry back wave model.
It's a lithium-ion polymer. And then I just I encased all the circuit and the battery and so. So for the results of the jellyfish, this is the first untethered jellyfish-inspired robot that's based on free-strain-free DEAs. And then also it's the fastest untethered jellyfish-inspired robot based on DEAs. The last word was 5 millimeters per second, and then ours is a little bit faster, about 6 millimeters per second. So it's a big improvement, but I'll take it. All right, I want to switch gears slightly now. Actually, that might be funny to tell you in a minute. To our cephalopod-inspired robot. And so our the way that cephalopods swim is that they have this mantle cavity at the front of the robot. Sorry, of the animal. Maybe not relax too much. All right, so you have this mantle cavity, and then you have this this area here where fluid can come in. So when they swim, when they want to use jet propulsion, what they'll do is they'll hyperinflate their mantle cavity, sucking in a whole bunch of water. And then when they want to eject it, they contract all those muscles and they push all that water out through this funnel. Okay? And they show that the nozzle can be turned in any direction, so it enables the squid to swim in any direction, even backwards. So I briefly talked about it earlier, the added mass effect. And so one of the advantages of having a body that can change its shape during swimming is that you get this additional acceleration based on the change of your mass or your volume, really. And so there's what happens is that if you're pushing a body through the water, so say you're pushing a ball through the water. If it's a big ball, it's hard to push because there's a lot of fluid that you're accelerating as you're pushing the ball. If you push a smaller ball, you're accelerating a smaller amount of fluid that the ball is displacing. And so if you can actually dynamically change the size or the volume of the object that you're pushing through the water, you actually get an acceleration from that. I couldn't find a good picture, so that's why I got that. The other thing that we were looking at is the formation number. Okay, and so what this says is that if you have a pulse jet it's most efficient at some certain ratio of the length of the jet to the diameter of the jet. And so one way of calculating that is this here, the formation number. So we have, it's 4 times the change in volume divided by pi divided by the diameter of the jet. And so what this means is that for high formation numbers, so say for example for cake, you get this very disturbed, very turbulent looking jet. But what you really want is something that's very smooth. So you want the leading vortex to be able to be stable and pull in as much surrounding fluid as possible to make it the most efficient. And so this stability happens right around 3 or 4 for this ratio. So here's a plot from Professor Shu, who's in the back. So if I'm making mistakes, be sure to shout it out. So we have, as a function of formation number here, we have the speed, velocity, and then the length. And then after we have the energy for swimming, and then the efficiency. And so you can see that the velocity is at a maximum right around formation number 4. So what we want to do is we want to make our robot as efficient as possible. So one way that we can do that is by changing the diameter of the jet that we're ejecting. So there's been 2 groups that have been working on the atom mass, or that have showed experimental robots with the atom mass impact and formation number discussions. This first one is an elastic membrane that they've hyperinflated with water around a 3D printed structure, and then they release it. The trouble with this is that it's not repeatable. So each time they want to make the swim, they have to go and hyperinflate it again. And then this other one, they did have a cyclic actuation strategy. So it was able to, they have tendons on the inside that are squeezing or compressing this soft body. But this guy, it's tethered, and then if there's not a big change in the overall volume, so they're not really taking advantage of the atom mass effect in a big way. So we wanted to see if we could build on these 2 examples and make something that was a little bit faster and more efficient. So the hypotheses that we have for this project are that we could design a split gear mechanism to enable slow storage of elastic energy and a rapid release of it. We say that buccal beams and elastomeric skin can store sufficient elastic energy to drive the full jet propulsion, and then that the thrust of the robot can be optimized for the right ratio of the formation number, or the jet length. And valving could be used to provide unidirectional flow, which will improve the performance of the robot. And lastly, that we could use angled nozzles to turn the robot based on thrust vectoring. So here's the schematic of the robot. So we have, on the left-hand side, we have the nozzle, and then we have a bottom and a top end plate that are 3D printed, and then there's a rack that connects the top end plate, that's connected to the top end plate, and then on the bottom end plate we have the motor mount that has a DC motor that has a gear on it, and the gear is missing teeth. And so what happens is that as the gear spins, it will pull these 2 parts together, storing elastic energy in the flexible ribs, and then once the teeth slip, then it can quickly spring back into its original shape. So here's a breakdown of the actuation. So right now it's inflating and sucking in water, and then when the gear slips, then it releases a jet of fluid and swims forward, and then it will do this over and over and over. Here's a video of it actuating. So you can't quite see the gear because the teeth, or so the ribs are including it, but you can see it actuating. And so here's a typical example of the velocity profile normalized to time. And so during the retail period, it's slowing down as it's sucking in water, and then once the teeth slip, then it starts shooting out the water and begins accelerating and stuff. We wanted to see if we could measure dependence on thrust for formation number. And so we tested it by putting the robot on a load cell to measure the amount of force that we can get out of it, and then tested it at different frequencies and for different nozzle diameters. And so what we're doing here is that we're keeping the change in volume constant. So the 2 variables for the formation number were the change in volume and then the diameter of the nozzle. And so we're keeping the change of volume constant and then just tuning the nozzle diameter. And so for the smallest nozzle, which is 20 millimeters, that corresponds to a formation number of, I believe, about 40 or so a very high formation number. And then as the nozzle gets bigger, the formation number gets smaller. And so the black dots, which are 50 millimeters in diameter, it corresponds to the nozzle that's 50 millimeters in diameter, has a formation number close to 4. Okay? So we would expect this to have the most amount of thrust, which is what we see from this test. Another way that we can measure the efficiency or the performance of the robot is through photo visualization. So in this, we're injecting the body of the robot with a dye that we can visualize using a high-speed camera. This is at regular speed, and we can also, instead of a blue dye, we can also use a fluorescent dye and measure the vorticity that way. And so here are high-speed videos of the jet. And so in this case, the formation number is very high. So what you have is a stream of fluid that's moving so quickly that it doesn't have time to roll into a stable vortex ring. For the middle phase, it's closer to the ideal formation number. So you get this leading vortex ring that starts rolling up, but then there's still more fluid that's coming in behind that leads to secondary vortex rings. And then the final case, when we have formation number close to 4, we get this nice stable leading vortex ring, and then almost all of the fluid that comes out is then trained in that leading vortex ring. So that shows that this is the most efficient for this robot. All right. So now that we've tested and designed the robot to have the most amount of efficiency that we can get, we want to make it untethered. So I designed this waterproof housing for the electronics. So it's just an acrylic tube with a waterproof switch that you can turn on and off, and then there's a dome, a clear dome at the front of it that you can put a camera in or other sensors that you want. And so we also want to look at valves. So in squid, they have one-way valves where they can direct the flow to come in through one side and then out through the nozzle. It's more efficient than having fluid come in through the back end and then back out the same nozzle. So we want to look at if we can make nozzles to get more thrust. This is a CAD rendering of the design. So it's just a really simple design where we had small holes around the perimeter of the nozzle and then a passive flap that controlled the direction. And we measured the thrust for this one. With the nozzle, it was similar to without the valve at high frequencies, but we had better performance at some of the lower frequencies. So here's a video of untethered swimming. So we have the waterproof power supply on the front of it, and it's swimming through the water. And then we can measure the average speed per cycle as a function of formation number. And so for very low formation numbers, so you can see here there's kind of a trend where at low formation numbers, it's slower. At high formation numbers, it's slower. And then when formation number is close to 4, we get the maximum speed measured. And then the passive valve that we designed here didn't really improve the performance, but we're still working on trying to improve it for improving performance in future work. So that was untethered swimming. Yesterday, I took this to Birch Aquarium and got it to swim in the water with their fish down there. I didn't get to go through and get the best videos, but here's one of the better ones. It's swimming through one of their tanks and stalking this fish, which didn't really seem to mind it too much. And then from the GoPro footage, we have the fish bottom right, and we're going to make a little loop and follow the fish around. And you can also see the divers that are cleaning the tank. Yeah. So this is turning because the flow in the tank is pretty fast, but we want to also see if we can actually control the steering of the robot. We didn't have time to do dynamic steering for this project, but we wanted to at least prove the principle that we could steer it using cross-vectoring. And so we have nozzles that are printed at different angles. So they're up on the table if you want to look at them afterwards. And so this is with a 17-degree angle. We can get clockwise turning and a pretty big loop. And then if we have a nozzle that's twice the angle, we can get tighter turning. We can get it to turn on its head. And then if we have it going in the other direction, we can get counterclockwise speed. Okay, so there's just a proof of principle that we can steer the robot based on the angle of the nozzle. So the results for this are that we achieve both pulse jet propulsion and an acceleration based on the added mass effects. That we demonstrate the dependency of both thrust and swimming speed based on the formation number. That we developed a straightforward, reliable electromechanical control system that enabled untethered propulsion. We demonstrated control turning through thrust vectoring. And so as kind of an overview of the 3 different projects, so they went a little bit faster as the research went on. So for the eel, the top speed was about 2 millimeters per second, jellyfish was 3.2, cephalopod was 184 millimeters per second. We can also measure that in terms of body length per second, which is another way of comparing it to different animals or different robots, seeing how fast moves compared to its body length. The thrust was similar for the eel and the jellyfish at 42 micronewtons, which is really, really small. And the cephalopod blew those out of the water. For the input power, the amount of power that it took to drive the robot, the jellyfish took 4 times less power than the eel did. So it showed that it was more energy efficient. And then the cephalopod took about 7 watts. So in the cost of transport, we did find the smallest cost of transport for the jellyfish-inspired robot. That increased for the cephalopod and then was much higher for the eel, which was not optimized for swimming efficiency. Then if you want to kind of tune the robots, we have the first 2 are silent and can be translucent or transparent. So if you want something that's silent, we can use DEAs, or if you want something that's more powerful, maybe you want something like the cephalopod-inspired robot. So the conclusions are that we were able to design artificial muscle soft swimming robots that are silent, transparent, elastomeric, and enable eel-like swimming. We developed an actuator that takes advantage of the energy-efficient motion of jellyfish to enable a low-power, untethered robot. And we demonstrated an actuation strategy for a squid-inspired robot that takes advantage of both pulsatile jet propulsion and the added mass effects. So the future work for other people. So for the eel-inspired robot, it would be nice if we were able to come up with an untethered platform for it to see if we can improve the performance of it based on including free strain, and then also exploring the impact of fibers to improve the performance of the actuator. So one of the issues with the actuator is that it bends more towards one direction than the other, and so our hypothesis is that if we include fibers, that we can actually improve the ability of it to swim the same or better in both directions. For the jellyfish-inspired robot, one of the key criticisms of the jellyfish that we designed is that there's a lot of space in between the lip heads. And so you have a lot of fluid that slips between the lip heads. So if we could decrease that distance, we could get more efficient propulsion as we can move more water around. And also we could make it molded so that we could actually start with a curved surface. So we can start with a hemisphere and mold it as opposed to going to this planar approximation. I think we can make it better that way too. And then for the cephalopod-inspired robot, looking at further optimizing the thrust and efficiency by improving the nozzle diameter and shape. So this is a very simple cylindrical nozzle that we have. And then also improving the selection material for the skin and the ribs. Developing a remote control and active steering for the project. And then lastly, implementing some sort of sensor payload. So right now we just have a camera in it, but we could also use it for other sensors as well. That'd be really interesting. So for acknowledgements, I want to thank funding sources, NSF, ONR, and NASA helped out for the other projects. I want to thank my committee members for their time and attention and expertise in being here. The collaborators that helped out on these projects, Dana for all that you do, and then the students that I was able to work with on these projects as well. There's a list of journal publications. The first 2 are the squid and the jellyfish-inspired robot, and then the 4th one is the eel-inspired robot. And then some of these other ones are other projects that I've collaborated on. And then conference papers. And with that, that's the end of the talk. So thank you very much for your attention, and I'll now take any questions that you have.
questions, I wanted to say one thing that I omitted at the beginning of the talk, and Caleb is being very humble here and not talking about the many awards he's won over his time here at UCSD, so I want to mention them briefly. Caleb won a National Science Foundation Graduate Fellowship in 2015, I believe. Was both a semi-finalist and a finalist for the UC San Diego Grad Slam in 2016 and 17. He won a first place Best Student Paper from the SPIE Smart Structures and DE conference in 2017, and was a finalist for the Outstanding Graduate Student Leader Award for co-founding a student organization at UCSD for robotics, for the Robotics, Contextual Robotics Institute, the students that are conducting this research. In 2017, one of the many students Caleb co-advised actually won the SACNAS Best Undergraduate Poster presentation in mechanical engineering, who is actually here in the back, Luis. So congratulations to both of them. And finally, in 2018, Caleb won a Jacobs Graduate Student Council Award. So many that I needed my notes. Hopefully, you're all very impressed, and now we can open up to questions. Yeah.
So in addition to the mass effect, where you're decreasing your mass while extruding the mass, when you do the inlet valve, do you think it'd be advantageous to position the valve in front so that if you're like banking to the right, like you might have the inlet on the left and then the valve going to the right?
Yeah, so we had talked about, and Professor Stewart, I think this step on. We had talked about putting the inlet nozzle on the front, and there's definitely some advantages of doing that. We didn't do that in this work yet, but I think it's definitely worth exploring. I hadn't really thought about putting it at different positions on the front of it to make it even more streamlined, but I like that idea. Thank you.
Or maybe related to that, can you explain to us, Caleb, why you think the valves that you did try didn't actually improve the performance at full speeds or the higher speeds?
Right, so I got props. So we took a very short pass, a very quick pass at just trying this. And so the design is pretty simple. So there's the nozzle in the center, and then the holes for the valves are just around the perimeter. So the size of the holes for the inlet are very small. So I don't think we're actually getting that much advantage of having it come in through these smaller holes. But then also the passive flap that we made, I think we could have further optimized it to better move, to be more flexible with the inlet water, and also to better close when the water goes out. So this was just a very first pass. It kind of demonstrates the idea that we could do it, but I think there's definitely more to be done to make it more efficient. Yes.
So while Jules, we've had some conversation.
Yes.
Wonderful talk.
Thank you.
I just want to make a pitch to transition these to things that we can use for oceanography. And it's not a question, but I hope you don't mind that making a comment. That what we really need are untethered, quiet, and hydrodynamically stealth vehicles. So any and everyone in this room who wants to work in this area, we at Scripps would love to have you help us in that development. And thank you for wonderful talking. And I'm wondering in 10 years where we're going to be. Yeah. And what are your thoughts on that?
I mean, we did this in 1 year, so we should be farther in 10 years from now. I think there's a lot of potential for this, especially this last platform, for having an experimental system that somebody like you could use out in the environment.
Thanks very much.
I saw there's another question. Yeah.
Very cool work. I'm interested to know which is the autonomy of these robots. How long can they perform?
Yeah, great question. So they're not. Let's see. So in terms of autonomy, there's no like steering or real control. It's just controlling the motion of it. We don't have any autonomy in terms of like making a turn or responding to some outside stimulus. In terms of how long the battery lasts, it depends for each of the projects. I've got it in my notes off the top of my head, but they swim for several hours. So like the squid, we can do a full hour of testing without too much change in performance. It also depends on the battery that we choose for it.
So maybe you could explain in terms of increasing the level of autonomy of the squid, what would be required? I don't think you really talked about that.
Yeah, so great question. So glad you asked. All right, so for the level of autonomy, so first off, we need active steering. So that would be one of the first things that I think that.
What sort of additional components or things that you need to do that?
Yeah, so for steering, so right now I don't really have any sort of microcontroller on board. It's basically just a battery that's plugged into the motor that causes it to spin at a fixed speed. So we would need to first include a microcontroller that can better control the actuation of it, and then also provide some sort of signal for steering, and then also have some inputs for whatever sensors that you're using, whether it's visual, like the camera that we have, or we're trying to respond to some other analyte instead. Like maybe wants to go towards temperature gradients or pH gradients instead. Or light. Yeah. Oh, go ahead. Okay, go ahead and
Okay. Good work. And as we know, Mississippi Group also developed jellyfish-inspired macron robot recently, right?
which one?
Native City.
Oh, yeah. Just
yeah. It was actuated by magnetic field. But I think it is at the size of a millimeter. What about your size? The jellyfish?
Great point. That was one of the things I meant to correct on my slides and then forgot to add the legend to the scale bar. But
the
yes.
question is that how did you decide how did you set the size of the system, your jellyfish like robot? Have you do some optimization about the size? If you scale it down, what will happen?
So one of the constraints that we have with this fabrication approach is that we need the border. So the way that I'm designing it now, we have the border that sticks to itself, and the border needs to be a certain thickness in order to prevent leaking of the fluid and to prevent dielectric breakdown between the layers of that of the material. And so we have a specific size for the border, and that kind of determines a lot of the rest of the size for the robot. So right now, the border is about 8 millimeters in diameter. And so the total robot here, if I, for the jellyfish, I don't remember the exact dimension, but it's oh yeah, so it's, should be just under 12 inches square. So 12 inches by 12 inches.
Are you saying that there's a limit and then how small you can scale it because of like the standard sizes or proportions of the materials you're working with, or like if I use a smaller robot, I use thinner materials, smaller voltages?
Yeah, exactly.
There's a limit to that. Or the hard constraint was what you had at hand.
Right. So the hard constraint for this project was my fabrication approach. But if you use a different fabrication approach, you can have smaller borders, and then you can also have a smaller robot overall. So like if you did molding, you wouldn't need to be worried about having such a big border. We haven't need a big border because we're just laminating 2 layers together. But if you molded the whole thing where there's no seams, you could make it much smaller.
So there is work that has made very thin DEAs, right, and very low voltage.
Yeah.
Can you say a little bit about how it's possible to bring down voltages required?
Yes. Yeah. So there's an interesting group. So at Harvard, they have an acrylic elastomer that they can. They can get very, very thin layers of their elastomer. So it's similar material as the VHB that we're using. With the VHB, we have specific layers because that's what they ship to us. But if you can get it in a in a curable form, then you can actually spin coat it and get really thin layers. And also they get the advantages of having the performance of an acrylic elastomer, and then also the advantage of being able to control the thickness of it, so you can have very, very thin layers. Which means, so you can use lower voltages and get the same amount of pressure. Other questions? Yeah.
Questions kind of about the kind of control and also the manufacturing part.
Yeah.
For the jellyfish, it's all it's basically one actuator. Is that right?
Yeah.
Right. Just so it's all connected. So I noticed that there's some asymmetry when it's actually activated. Some of the lights don't seem to move as much.
Yeah.
Like, is that a manufacturing problem, or is that something that I guess is that an issue, or like the jellyfish only have like one muscle?
Yeah, so a couple of things there. So the first off is, so jellyfish have generally one muscle that leads to contraction, but they do also have muscles around the edges that they can control the steering. For our case, what you'll see here, and one of the examples is like, so in this top video, if that's what you're staring at, the back one, it's not actuating at all. That's because there's an air bubble that's occluding the water. So the fluid electrode can't get to the top of that in this example, and that's why it's not bending. Another reason is that, so some of them will bend more than others because of the way that we've made them. So just imperfections in our fabrication. And then if you were referring to the tethered case, the tether itself kind of restricts the motion of some of the mopeds. And so as it's swimming, it's bending around where the tether is. And also if the mopeds or the fingers or arms or whatever you want to call them are running into each other, that'll also change the way that they swim. But I think what would be interesting is that if we make this in such a way that you can address each of the pads or each of the channels, then you could actually do active steer. So where, so the hydraulic example that I showed at the beginning, they can control at least left and right. They can actuate one side and not the other to spin one way or the other. So I think it would be interesting if we could do that, but we haven't been able to do it like that.
So you explained that there were some losses in efficiency in like fluid escaping between the fingers. Biologically, do jellyfish, do they have this sort of this differential forces to squeeze their bell? I always thought it was more like a sphincter, like they have like this canonical squeezing effect, and that way there's not like this differential between the two outer layers of tissue. Is that something you had to work with, like because of the materials, or like would you prefer something like where the entire bell just canonical squeezes?
I would prefer the last case where the whole bell squeezes at once and where we have a full hemisphere and no fluid that leaks out the side. And so what we're showing here, this design is based on the larval stage or the baby stage of jellyfish, where they still have separate lappets or petals. And that's why there's fluid that leaks in between. But then as they grow, as they get older, the material closes around, and that's how they get a solid bell structure. But for our actuators, without any pre-strain, we didn't have enough force to actually deform a full bell. And so we weren't able to emulate an adult jellyfish. We were only able to emulate a baby jellyfish that has these separate structures.
Do adult jellyfish still have like these ligament or these fingers in the webbing? Like I don't know. I thought it was like a continuous.
That's my understanding as well. Yeah. Yes, in the back.
I have a question about the real-life motion.
Yeah.
So you show us the few pictures. I wonder why the strain of stress is related to oscillation instead of the Young's strain modulus?
Oh, it is both. So the Young's modulus was in the denominator. Other questions?
Yeah, maybe you could explain why the Poisson ratio is relevant to the amount of strain you get.
So, yeah, so we're relating we're relating the pressure that you're applying in the z direction, and then what I was reporting there was the strain and the x, or the lateral direction. That's why the Poisson ratio.
Okay, so because our committee members are going to have to leave at some point. If there are no more questions, I will ask everyone to step outside.